For some, it's the most important element of the 21st century, the white gold of the green economy. Lithium is a strategic resource in the energy transition, and you're going to hear a lot about it. Especially since by 2028 one of the largest lithium mines in the European Union could open in France, in Allier. This site could produce about 34,000 tons of lithium annually for 25 years, enough for 700,000 electric car batteries. The goal is to lessen reliance on imports of this vital element, needed to shift away from combustion engine vehicles, and whose global production is terribly concentrated. Nearly 2/3 of the world's accessible resources are concentrated in the lithium triangle in the Andes Mountains. So, I can't help but wonder why some states seem to be sitting on piles of white gold and others are not. How is it that there are places where it's worth digging to find rare metals and others where it's pointless? And you'll see that looking for an answer to this question will take us to some of the hottest places in the universe, all the way to the center of stars about to explode and close to the Big Bang itself. First, let's consider a somewhat unsettling idea. On a planetary scale, no element is truly rare, but most are extremely diluted and hard to extract. Let's use the most iconic example to illustrate this. Precious metals like gold are found everywhere, even in your garden, because gold isn't truly rare. It's just very hard to extract and highly diluted. In the Earth's crust, the average concentration of gold in the rocks is estimated to be about 0.005 parts per million. So if you were to try, just as a figure of speech, it would be a strange hobby. Using tweezers, shovels, and large processing plants, you could recover about 10 kilograms of gold from a 100-meter cube. Spoiler alert, you wouldn't be able to do it, it would be too complicated to pull off, and on top of that, it would cost a fortune. The main challenge is always finding deposits concentrated enough to mine. By the way, it's strange to think that if you have a little gold at home, there's a good chance a large part of it comes from here. Nearly a quarter of the world's gold in circulation comes from the Wheatwater Strand Basin, a South African region with a hard-to-pronounce name, covering just over 1/10 the area of France. Since the first vein was discovered in the late 19th century, over 40,000 tons of the precious metal have been extracted. Obviously, that doesn't mean that a very large part of all the gold in the world is found exactly there. What distinguishes this basin from your garden soil is mainly its abundance and concentration. At Wheatwater Strand, metal in the rocks is 1,000 to 10,000 times more concentrated than average, unless you live in a gold mine. Do you realize that a quarter of all the gold in the world comes from an area barely smaller than Belgium? That's because unique geological conditions combine to allow such a concentration. The discovery of so much gold in one region required a unique combination of geological events. Here, several billion years ago, a continent rose up, forming from rocks rich in heavy metals that came from deep within our planet. It created huge mountain ranges that, after millions of years of erosion, deposited some of their gold in a shallow inland sea, where, for millions more years, thousands of meters of sediment rich in precious metals accumulated, and then these sediments were gradually covered by several kilometers of lava, compacted and buried. These unusually gold-rich layers were baked into rock and stayed buried for hundreds of millions of years until about 2 billion years ago. A huge meteorite, more than 10 kilometers in diameter, crashed into these layers of sedimentary rock, creating a crater 300 kilometers wide. The impact structure is still visible today from space. By lifting and overturning the underground strata, the meteorite brought some of the gold back to the surface. So it is believed that without this major impact, the gold deposits in this region would have remained buried several kilometers deep and would certainly not have been discovered yet. In the late 19th century, prospectors first struck their pickaxes on a treasure barely exposed at the surface. 2.5 centuries later, extraction still occurs underground. Because by following the inclination of the veins, the miners eventually worked in tunnels, the deepest of which are located nearly 4 kilometers below the surface. On the other side of the globe, in Canada, we find in the Sudbury Basin the second largest known impact crater on Earth, which, for other reasons, has also made this region one of the world's largest suppliers of nickel, copper, platinum, and palladium. Except for iron, aluminum, and a few others, most metals exist in rocks in tiny amounts. Many of them are only present at concentrations of just a few parts per million, and that's where it gets fascinating. To find them in large amounts in one place, Earth must have provided the right geological processes. Also, through associations, chance, and chemical affinities, various minerals concentrating these metals can form. Now, the existence and diversity of existing minerals has been, let's say, quite eventful. It hasn't always been what it is today, by the way. Contrary to popular belief, most of Earth's 5,400 mineral species are relatively recent. Considering the age of our planet, we believe it's about 4.5 billion years old. At the time of its formation, the primitive Earth must have been made up of only about 60 different minerals at most. Then, very quickly, that number began to skyrocket, because the heaviest elements sank to the center, forming Earth's metallic core. On the surface, the continuous leaching caused by rain created, in just a few million years, a cascade of new combinations of new minerals. The number then rose to about 250. Then, as the planet cooled down, and with the onset of plate tectonics, that is, the movement of the crust on the surface, new processes began to emerge. Sometimes the Earth would concentrate its rarest elements by partially and repeatedly melting some rocks from Earth's crust and mantle. The volcanic activity of our planet will, over time, concentrate rare or uncommon atomic elements in the magma, eventually allowing the formation of new exotic minerals. It is believed that nearly 1 billion years of tectonic and volcanic activity were necessary for this continuous reorganization of the Earth's crust and mantle, with the help of these repeated burials and meltings to eventually reach, in some places, concentrations high enough to form nearly 500 new minerals. From this view, we're fortunate that Earth, unlike Mercury or Mars, retained enough energy during formation to still have surface tectonic activity. Because this makes our planet a celestial body capable of concentrating elements and producing a large number of rocks and minerals over time, right above the subduction zones, where heavier plates dive beneath the continents. Significant deposits can also form because the tectonic plates that carry surface rocks deep down increase the pressure and temperature of the minerals they contain. Some elements can be leached out by hydrothermal fluids, or even transform or begin to melt. And then, magma concentrated and enriched with rare metals slowly rises back to the surface. That's why many of the richest metallic ore deposits are found near volcanoes in subduction zones. Just think, Chile alone is said to hold nearly a quarter of the world's total copper reserves. These dynamic processes and repeated reworking of Earth's crust and mantle will raise the number of minerals on Earth's surface to about 1,500. Of nearly 5,500 minerals, 1,500 formed directly from Earth's activity, while most others appeared indirectly because of it. If I'm showing you a cyanobacterium, it's because living things indirectly helped form almost 3/4 of known minerals. Let me explain when living organisms, such as cyanobacteria, started to perform photosynthesis and proliferate. 2 billion years ago, there was practically no oxygen molecule in the atmosphere. Now, performing photosynthesis releases something we like to breathe, namely oxygen. And you may have noticed that oxygen oxidizes, it makes butter go rancid and iron rust. Thus, following the appearance of large numbers of these photosynthetic organisms, the atmosphere and the oceans slowly began to fill with oxygen. And this oxygen reacted with everything it could oxidize and forever changed the mineralogy of our planet's surface, and the world literally rusted in the oceans. Oxygen and dissolved iron formed ferric oxides, which precipitated and accumulated for millions of years. So much so that the banded iron deposits from that time provide nearly 90% of the iron ore mined today. The great oxidation ultimately tripled the number and diversity of minerals. Sometimes evolution is a revolution in disguise. And I don't know about you, but personally I think that's absolutely amazing, that most of the minerals present on Earth today indirectly owe their existence to the development of life. So, to sum up, it all depends on the rarity of each atomic element in the Earth's crust, the types of minerals they become part of, and the geological processes those minerals are associated with. We end up at the end of the chain with mines whose metal content varies greatly. Iron and aluminum mines extract rocks containing almost 50% of these metals, which is pretty normal since these two elements are among the most abundant in the Earth's crust. whereas a deposit containing 2% copper ore will be considered exceptional. Getting 20 kilos of copper per ton is great. Over 200 grams of silver makes you even happier. If the ground under you has just 0.005% gold, are you sitting on a fortune? Because deposits with 5 grams of gold per ton are considered high grade. As for the lithium mine in Alia, its average lithium oxide content is 0.9%. That may seem low, but it's actually quite a lot. Excavating several hectares over 100 meters deep yields hundreds of thousands of tons of white gold. In short, as you can see, that's why precious or strategic metal deposits are so unevenly spread worldwide. Throughout Earth's history, it often took a rare combination of processes to concentrate these elements in enough quantity. And whether these processes happened slowly over millions of years, or took place suddenly in the violence of a meteorite impact or a gigantic volcanic eruption, it's always the forces of nature that have done most of the work for us. If you complain about the low gold or lithium concentrations in your backyard, you shouldn't just blame geology. You should blame the whole universe too. When you think about it, none of the geological processes we've discussed create atomic elements. They simply change their proportions, their arrangements, mix them differently, and thus create new minerals. Minerals that transform, dissolve, melt, or break apart by exchanging atoms, which are far more solid than rock. Atoms can't be created or destroyed under earthly conditions. They've all existed for at least 5 billion years. To trace the origin of gold or lithium, we must look even further back in time. These elements' story began long before the ground we stand on was formed. In fact, as strange as it may seem, absolutely all the atoms present on Earth today come from space. They have a truly extraterrestrial origin, and among all these atoms, those of lithium and gold certainly have the most extraordinary origins. It's been more than half a century now that we've known stars don't just emit light, they're also factories that transform matter. In the cores of these stars, atomic nuclei collide and fuse to form new elements, producing nearly all known atoms. In this sense, we are literally surrounded by and made of stardust, and that's not just poetic license. You have stars in your eyes, which are mostly made of atoms created by stars. Since each atomic element requires very specific pressure and temperature conditions to be forged, they obviously don't all have the same history. Some formed in the cores of sun-like stars, while others developed in the outer layers of red giants nearing the end of their lives. While others, like aluminum, were formed extremely quickly during spectacular explosions called supernovas. And following the collapse of giant stars, the traces of these explosions are scattered across the sky, where they can be observed with our telescopes. Supernova explosions create drifting filaments containing newly formed atoms that never existed before. Think about it the next time you use aluminum. All this metal was created by the explosion of giant stars billions of years ago. But gold, like lithium, might have an even more remarkable origin. To create heavy elements like gold, uranium, or platinum, you need forges even more hellish than supernova explosions. Only neutron star mergers can explain the formation of large quantities of such metals in the universe. It has been estimated that when two neutron stars merge, no less than 10 times the mass of our planet in pure gold can be created, before spreading out and dispersing into space. So that one day, a tiny part concentrated by geological activity ends up in one of our mines. So, if there is relatively little gold, platinum, or uranium on Earth compared to the amount of iron, nickel, or aluminum found here, it's because these heavy metals require, for their formation, the occurrence of extremely rare events which, although among the most violent observed in the cosmos, are so rare that they produce only the equivalent of a drop of ink of matter diluted in an ocean of space. The lithium atoms we eagerly extract from Earth may have an even more unique origin, because almost all the atoms around you, including those that make up your body, have had to pass at least once through the heart of stars. Lithium is an exception. Far more fragile than other atoms. It rapidly transforms into other elements in the intense heat at the core of stars. And the lithium present on Earth is formed in 3 very specific ways. Some of it was born in the great cold of space from other atoms that were struck by high-energy cosmic rays. Another part of the lithium was formed in the cooled outer layers of red giant stars at the end of their lives, while the last part simply formed. A few minutes after the Big Bang, as the universe cooled enough for primordial nucleosynthesis to start, the formation of the first atoms. I'm not making an episode on atom formation or explaining how or why it happened. It would take too long. I'll put some links under the video and we'll soon make an entire episode about the Big Bang. The important thing to remember here is that a significant portion of the lithium atoms we extract from the Earth are almost as old as the universe. So, the lithium in our rechargeable batteries comes from very far away in space, and especially from very far back in time. Extracted by miners from Earth's mineral-rich depths, refined by skilled technicians and engineers, it originated from atomic elements formed through giant stars' life cycles, cataclysmic collisions, and the Big Bang. And among these precious remnants from bygone eras, there is a metal, lithium, which is at the heart of a new technological revolution undertaken by mankind, a technological revolution known as the electric battery revolution, which will bring its own set of challenges, starting with the amount of available materials, because lithium is only the 33rd most abundant element on Earth. On average, there are just 20 grams per ton of rock in Earth's crust. And even though nature has allowed it to be highly concentrated in some places, like in South America, where many geological processes combining subduction, volcanism, and erosion have, over millions of years, created a region where finds, spanning Chile, Argentina, and Bolivia, nearly 2/3 of the known reserves of this precious element. The hardest part remains to be done today, all around the world. Mining conditions are growing more complex as the average metal content in ores keeps decreasing, which is logical. We always start by targeting the richest and most accessible deposits that we know of, and when those are exhausted, we move on to the second-rate veins. In Chile, the copper content in new mines has halved over the past 30 years, which could become a major future problem. This means we'll need to use more energy to extract deposits that are less concentrated and deeper underground. At the same time, the demand for metals keeps soaring. According to the International Energy Agency, the demand for lithium alone is expected to increase 40-fold by 2050. These staggering proportions apply to nearly all metals in the energy transition. It's estimated that in the next 25 years, we'll extract as many metals as humanity has since antiquity. The piles of rock that will be extracted from the Aliyah mine will only make up a very small part of what we import each year. In my view, they will at least make us look more closely at the problem. However, all our technological devices require extensive digging for their production. This makes me think producing lithium in France avoids hypocrisy and the ostrich policy. This means importing pollution and having others produce or extract what we don't want at home. Afterwards, and still, from my necessarily subjective point of view, I think that even if the opening of this mine is an opportunity to bring back into the debate what this kind of operation involves, from an energy, human, and environmental point of view, it will only marginally change the true nature of the problem. Namely, our raw materials are limited, and unlike a few rare countries, we don't have a geological jackpot. Even with hard work and excavators, achieving sovereignty over all strategic raw materials seems very complicated. At the time of peak oil, moving away from fossil fuels quickly is essential. I wonder if. The real question may not be whether our subsoil has enough of a certain element. Instead of questioning if our intended use for this valuable material is relevant, what will it be used for? In fact, even though nature has done most of the work to create and concentrate metals, I think maybe that's where most of the work remains. For humans, it's less about extracting materials and more about asking, what is it for? Personally, I keep wondering if it's really ethical today to manufacture individual electric vehicles that weigh several tons and can go 180 km/h, when we know perfectly well that such a car requires nearly 4 to 6 times more metals than a conventional model and contains nearly 80 different atomic elements. Is an SUV truly worth stardust? Do we really need all of this? In short, this mining project in Aliyah raises major questions, and addressing them all here would likely take as long as walking across it. That of the Grasberg open-pit mine, one of the largest open-pit gold mines in the world. To learn more about the lithium mine project in Aliyah, the National Commission for Public Debate is holding a major public debate until July 7. You can join this major debate by submitting an opinion or question to the project manager on the public debate platform. The project manager has 15 days to respond. I'll put the link and more information below the video. On the Science de Comptoir channel, you can explore the impacts of large-scale mines and learn why they occur. Extracting an element is difficult, even with several kilos per ton of rock. On Monsieur Bidouille's channel, you can explore the major technological and industrial challenges of bringing an element from the mine to our batteries.